My name's Ty Newell, and this video is to look at how to make a restaurant a COVID safe space. Using the COVID safe space IAQ calculator, you can determine relative to the size of your restaurant and activity level what changes you might need to make that a COVID safe space and what impact that might have on your ventilation costs, on your activity costs within the space. As you follow through this series and the other introductory videos, you'll see that there's a wide range of interacting input with two primary results. We want to know first whether or not the infection probability, that is, for any of us who might be susceptible, our chances of catching the disease from an infectious person might be. And then, second, how many people that infectious person is likely to make sick. And it's this infection multiplier that's the most important as far as stopping the current pandemic. We need to get the infection multiplier below 1 in all indoor spaces. When the infection multiplier drops below 1, that means that that one infectious person is no longer able to make another person infectious. But currently, and unfortunately, too many of our spaces, that one infectious person might make two people infected, might make four people infected, might make 10 people infected. And we have to stop that to stop the disease. So the COVID Safe Space Calculator, it's a communication platform. It's meant to be a common ground where building science experts, facilities, personnel, owners, employees, and staff, and most importantly, customers, a common ground where you can discuss in quantitative terms the actions you're taking and how that makes them safe. And with this tool, my hope is that you, as an owner or a manager of such a business, that you can talk to your staff and gain their confidence that these things are being done, and here's how that will make them safe. And to your customers, who, regardless of what actions you take, if you're unable to explain to me why you now have a safe space and do that in some manner that's quantitative, I'm not likely to return. I'm just going to think you're waving your arms in the air. And so to me, it's important that you have a basis for the actions you're taking and that you can explain why these actions will be effective. Now, in terms of restaurants, we ran an interesting experiment last fall. Colleagues of mine at the University of Illinois in the jazz performance and in the Department of Civil and Environmental Engineering, they both brought their instruments, their musical instruments, and their scientific measurement instruments to a local restaurant and bar, the Iron Post, typical of a venue in many communities and one that we'd like to have open up and be safe. And we set it up so that with the restaurant's own exhaust ventilation system, we could change the level of fresh air moving through the space, and also with a recirculating filtration system that we placed on the bar, that we were able to remove room air, take it through a MER 13 filter, and then with the measurement instruments, being able to measure particulates down as small as zero point 0.3 microns in diameter. But over the expected range that we sneeze and cough, and then that we respirate through our breathing, that we could measure the size of the particulates and their density in this air as we change the fresh air ventilation level and change the filtration level. And so it's a realistic venue and real measurements to see that what we recommend doesn't happen in the field. So it was getting cold out last fall. I'm a jazz fan. I regularly go to the Iron Post to listen to jazz. And about October, as it was getting below 45 degrees, a lot of our favorite musicians were braving the cold but it was hard to be comfortable. I don't know how their fingers moved on their instruments. The one good thing was that your beer didn't get warm, but it was time to move indoors. And fortunately, at the University of Illinois, we have the most advanced testing program anywhere, and I mean anywhere in the world. Our students, faculty, and staff test twice per week. You get the results immediately, but it allows for the extensive tracing and tracking that's needed to also stem the tide of this disease. But what that also means is that we have a pool of COVID safe people to use for test subjects. And among us, we got a crowd of about 20 to 25 people to gather in the iron posts, set up the instruments for monitoring the particulates and the carbon dioxide, and then had a performance. We had a wonderful 2 hour performance by two of our great University of Illinois student jazz bands. And so during that time, we sat in a largely vacant space. Most of the tables and chairs have been set up. And the owner, who at that time was allowed to have 25% occupancy, but the reality was everyone's afraid to go indoors. Without some knowledge of what's being done indoors, it's like playing Russian roulette. And so, even though they have an occupancy limit of 110, it's limited to about 25, and that's what we gathered for this test. And we collected data. And the data, while this is a fairly busy plot, the three most important plots to follow, uh, where the performance began, where you see it says fresh and filter, but the starred data points are occupancy. And you can see at about 2:30 to 3, people started coming in to gather for the performance starting at about 3. We got up to about 25 people. And then also increasing with the occupancy was the carbon dioxide. The carbon dioxide level went from about outdoor levels of 400 or 500 parts per million of carbon dioxide and rapidly grew with occupancy. And that's because the carbon dioxide we produce from our respiration goes directly into that room air, and it picks up very, very quickly. So even though this is a small fraction of what that restaurant would have on a busy night, it's indicative of how fast the air inside of a building changes. It's not hours, it's minutes. Person goes in that space, the carbon dioxide is going to go up. And associated with that carbon dioxide will be respiratory droplets just from your regular breathing that you're going to exhale very, very small droplets in this submicron range. And a human hair has a diameter of about 100 microns. So zero point 0.3 microns is less than 1% of the diameter of a human hair. And then for those time periods when somebody is coughing or sneezing and shearing off bigger droplets from the liquid film that's in your throat, these droplets were more in the, say, 5 to 10 micron range. But as has been shown by field studies, the predominant amount of virus release within indoor spaces tends to be these, for an airborne virus, tends to be these very small particulates, these submicron droplets that you can't see, you can't smell. There's no indication they're in the air, and you're never ever going to smell a virus at a level that will make you sick. And so the red line shows how the very small particles, we have particle data for zero point 0.3, zero point 0.5, all the way up to 10 micron. So a very refined set of data. But the zero point 0.3 I've plotted just of more interest. And you see how the zero point 0.3 particulates increase in density along with carbon dioxide in a manner that correlates with the activity, with the number of people inside the building. Now, what we're interested in, because these particulates are where the viruses are spreading around and getting inhaled into your lungs and making you sick, We want to see that by increasing fresh air ventilation and increasing filtration, that we can reduce the number of these particulates. And we want to see that as they're reduced, other things like carbon dioxide, an important indicator of the amount of contagion in the air, that that's getting reduced. Now I have a picture of pig pen. This is often called the pig pen effect. In addition to these small particulates that are coming out of your respiration, we are emitting particulates in any case. Skin flakes and just textiles are getting abraded and rubbed and reduced, and dander and things of that nature. And other particulates that you've picked up along the way that are then being emitted out of your clothing as you go into a space. And so you do have this invisible dust cloud traveling around with you. And uh, by the most part, most of the particulates that we're measuring are these other particulates, and just a fraction of these are the particulates that are coming out of your lungs that may have viral matter on them if you're infectious. The most important result out of this, though, out of this study, is that when we switched on that exhaust fan and started increasing the amount of fresh air going in, you see the CO2 respond and drop. So even though we had about 20 to 25 people and the CO2 was on an increasing path, once we kicked on that ventilator and pulled air all the way through the venue, the CO2 dropped, and you also saw the beginning of a drop of the particulates, in this case, the zero point 0.3 micron. Then we hit a period where we turned the fresh air fan off, the exhaust fan off, but we started a small fan with a MER 13 filter that was pulling about 300 cubic feet per minute of air, and we had about 20, 25 people, so about uh, say 15 cubic feet per minute per person of air drawn through a MER 13 filter. And you can see that there's continuing decrease of the particulates, but once the fresh air fan was turned off, the recirculating air fan did nothing to remove CO2. The CO2 started to increase again, but the particulates started to drop. Now, these are two tools that we have to reduce the concentration of contagion in a restaurant, in a classroom, in an office, and other spaces. But this is more directly in a restaurant. And I just wanted to demonstrate that in reality, we have these very important tools to get the concentration of contagion reduced. And then when we turned on both the fresh air fan and kept the filter running, we dropped the particulates down to a base level. Then the show was over, people left, CO2 dropped down, contagion dropped down, and so it did everything it was expected to, but more importantly showed in the field, instead of in the laboratory, instead of in a computer model, that we can control these particulates that are carrying the disease through the air from person to person. Now with the COVID safe space calculator, we can put in these same type of effects. And let's say we have a restaurant that has about 111 people in it. One infectious person, 110 people who aren't infectious. And we need to take different viewpoints. The viewpoint of a customer who's in there maybe an hour or two, because that's who you need to convince that they're relatively safe coming into your business. And then the staff, your employees who might be there for a 6 hour, 7 hour, 8 hour shift, as well as yourself, the manager or the owner, that it's a safe space for you. If you're down and out, um, that's a serious impact on your business. And so, without going through the calculator, but follow through the calculator demonstration video to learn how to use the inputs and gain additional information. But inputting these various factors into the COVID safe space calculator, and then looking at what would be standard conditions. Standard conditions would, if you do have a ventilation system that maintains reasonable air quality, or what's called adequate air quality, You would have about 1,200 parts per million of carbon dioxide. And carbon dioxide is easily measurable and it's inexpensive to measure. About $200 to make this measurement if you don't have sensors in place already, and most of you do not. So standard ventilation would have you at about 1,200 parts per million. And standard air filtration, if you do have a recirculating air system that filters the air, most likely is a MERV 8 filter. And MERV 8 filters do not remove virus. You need MERV 11 or better. So starting with standard conditions and with everyone susceptible except that one infectious person, you actually find in this large crowd that as far as airborne transmission, that you're maybe only about a 3% chance of getting infected relative to that infectious person roaming around the room. But more importantly, that infectious person is likely to make about 3 other people infected. And when the infection multiplier is greater than 1, the disease is accelerating. It's going to continue its rampant march throughout the populace. We're not protected. The disease will continually spread in an uncontrolled manner. Now, as we increase fresh air, and the way we know the fresh air is increased is not by measuring airflow, it's by measuring carbon dioxide. Carbon dioxide is reduced to 800 parts per million. That means we've doubled the fresh air flow from 20 cubic feet per minute per person to 40. And at 40 cubic feet per minute per person, we've knocked down the probability that you're going to be infected almost in half, from about 3.1% to about 1.6%. And the infection multiplier has also been dropped significantly, but we're still an infection multiplier above 1. It's still not a COVID safe space. We add in an air filtration system and we take air through a MERV 13 filter that's capable of removing 90% of the viral matter from the air. And we see that now we start getting to a COVID safe space. The probability that you're going to be infected by an infectious person, if there's only one, if there's two, and you can try this in the calculator, or 3 roaming around the space, that changes things. But with a single infectious person in that space, you're not likely to catch the disease, and that infectious person is not likely to make more than 1 other person sick. You've hit herd immunity. We have herd protection. The disease should die out. But as long as the disease is traceable, as long as it exists in the community, it's important to add additional protection. Face masks are that protection, and face masks loosely worn, poorly fitted, and not very strictly enforced, say 50% face mask wearing with 20% efficient face masks, 20% efficient at filtering out virus, we drop the infection probability a bit more, as well as the infection multiplier. But when we go to much more enforced, much better human behavior in wearing the mask, and much more efficient masks, like KN95 masks, not certified in the same manner as the gold standard, the N95 mask, but more widely available and with just as good of an efficiency, but just without the certification label. And readily available for $1 to $2 per mask, and highly advisable to wear. When we're more effective at wearing more efficient masks, we drop this disease down to where there should be very little probability that if you're susceptible, you get infected, and then very little spread of the disease beyond this establishment. It will die out. Now let's talk about vaccines. We can't get vaccinated fast enough. The impact of vaccine in a restaurant type of environment is that as we increase the fraction of the populace, say 50% are vaccinated, so we start moving to the right in this table, And then when we have 75% of the populace vaccinated and they're now essentially immune from the disease, we see that first, the probability of catching the infection for susceptible people stays exactly the same. That is, if you're unable to get vaccinated or for some reason reluctant to get vaccinated, you're still at risk. An infectious person walks in that space, you have every bit the same amount of risk of getting infected as you did when everyone else around you was also susceptible. Herd immunity, herd protection does not mean in this space you're protected from an infectious person in any different manner. What it does mean is that the infection multiplier is reduced. So as we increase the fraction of the populace that's vaccinated and immune, we see that the infection multiplier just keeps dropping lower and lower. And the more the infection multiplier drops, what epidemiologists call the basic reproduction number, the more that drops below one, the faster the disease disappears from your community. Now, let's take a staff viewpoint. Your customers within 2 hours are uh, with not a lot of precaution, but still, to get the infection multiplier reduced among customers, we still need to improve ventilation. We still need to improve filtration. For the staff who are spending a longer period of time, in this case, maybe a 6 hour shift, but maybe it's 7, 8, 10 hours, that's important. And starting with the same standard conditions, the same 111 people, one who's infectious, 110 who are susceptible, we see that your chance of getting infected if you're there the whole time is now about 10% instead of 3%. So you have a much higher infection probability than your customers. And if you're infectious, you've got a greater chance of infecting your other staff members during that time span as well. It's much more difficult. It takes much more stringent action to make this a safe space for you, the owner and managers, and your employees, and to ensure that it is a safe space for them. But still, it's actions that should be taken in any case in every indoor space. You're not doing something exceptional with this space. As you go from adequate ventilation to healthy ventilation, you're doing other important things. So as we follow through what the calculator would show us, that doubling ventilation, which reduces carbon dioxide from 1200 to about 800 parts per million, and then adding significantly better air filtration, changing from standard MERV 8 to MERV 13 filters, that we make these important jumps, these important reductions in infection probability and infection multiplier, but still and especially effective mask wearing and efficient masks, good fitting masks, masks with low leakage are exceptionally important to get the infection multiplier well below one and also to get the infection probability for your staff and employees as low as is practical. And again, then as more and more people get vaccinated, become immune, the infection probability for those who are still susceptible stays the same. So an infectious person walks in this business venue, your chance, if you've refused to get a vaccine or you're unable to, that your risk is still the same. Herd immunity does not protect you if you're susceptible. And uh, likewise, as we saw before, herd immunity does mean the infection multiplier is below one. And the more we vaccinate people, the more the infection multiplier drops. The more it drops, the faster the disease gets out of our community. And once the disease is no longer detectable within your community, that's when you might safely take the mask off. Now let's talk about reducing the staff. and customers. Let's get down to maybe half the population that we had. So if we're at half occupancy, what we see as we take these same steps of dropping carbon dioxide to 800, basically doubling the fresh air per person, running air through a MER 13 filter, and then effective and efficient face mask wearing, we actually see that the infection probability, if an infectious person walks in with only 50, 55 people rather than 110 people, your probability of getting infected goes up. In fact, it about doubles. And so this seems maybe a little odd at first, but what you have to think of is that you're only seeing half as many people, and your chance of seeing an infectious person is also in half. So the reality is that with these same actions, that you got the same infection probability, and that the infection multiplier is also following a similar path. So you might wonder, well, why would I do that? Why don't I let everybody in? And there's a couple of reasons. First, this is for airborne transmission of the disease and the direct transmission of the disease, where the 6 foot spacing or greater is so important, so that when someone does cough or sneeze, and if they don't have an effective face mask, that form of transmission has been reduced. And so that's very important. The second is that as you try to increase your ventilation, there may be reasons why you can't do that at this point, or that physically the building is just constrained so you can't bring more fresh air in above a certain level. And if that's true, then this is saying that in order to get to 800 parts per million, by reducing the number of people allowed in relative to the amount of ventilation that you have available, that's how you get to this level. So that's kind of behind the scenes, and you have to look at some of the other results coming out of the COVID safe space calculator. But basically, in reducing the occupancy level in half or to a quarter, we've reduced the amount of ventilation air that has to be brought in order to get to a lower carbon dioxide level, a lower contagion level. And similarly, the less air we have to take through a filtration system. So if there's limitations on the airflow through the filtration system, that we can again effectively remove contagion relative to the amount of people in the space. But above all, as long as the contagion is detectable and exists within a community, we must protect those who are still susceptible as we get vaccinated. And so efficient and effective mask wearing is very important to finally snuff this disease out of our communities. So with that, in the restaurant environment, ultimately you do want to increase your fresh air. And the reason for increasing the fresh air is not because of the pandemic, but as you'll see in other videos, as we talk about air quality and we talk about energy and utility costs, that more people are going to want to visit your business because it won't smell as much. That is, these steps to make it a COVID safe space also make air quality dissatisfaction reduced. It also reduces the number of sick days from non-pandemic, from seasonal flus and colds. It reduces those, and that improves your costs by fewer sick days among employees, fewer customers getting sick to visit. And then finally, there's improved productivity, performance, and everything else, better brain function that goes with more fresh air. And so if you have any questions, comments, criticisms, please contact me, Ty Newell. You can reach me at Ty Newell, one word, at illinois.edu.